Welcome to the Math 1, Unit 7, Lesson 2, Summary Video, Food at the Fair. This lesson is a practice understanding task which takes concepts you've been working on and applies them to new situations. The purpose of this lesson is to practice combining linear functions using multiple representations, including function notation, graphs, tables, and contextual situations. At the North Carolina State Fair, John is an owner of 2 food booths. One of his booths sells cotton candy and the other sells turkey legs. The cotton candy booth pays $500 per day for food materials and $16 per hour for people to work the booth. The permit and materials for the turkey leg booth costs $700 per day and the labor costs $30 per hour. Both booths are open for 12 hours a day. We should highlight some of the important information. First, John owns 2 different booths. One sells cotton candy, one sells turkey legs. The cotton candy booth costs him $500 per day just for the materials and $16 per hour for people to work the booth. Notice that's combined for all of the people working, not per person. The permit and materials for the turkey leg booth cost $700 per day, and the labor for that booth is $30 per hour. And both of the booths are open for 12 hours a day. Problem number 1 says, model the total amount the owner is spending each day to operate the 2 booths. Use multiple representations such as graphs, tables, and equations. So if we look at the table for this example, we are comparing the hours to the cost, to the total cost that it requires to operate each booth. So we can see that if no hours, the starting cost before they even open up the booth and hire people to work the booth for the cotton candy booth is going to cost $500. That's just a flat rate there. The turkey leg booth is going to cost $700 before they even open. And then at 1 hour of labor, it would cost John $516 to operate the cotton candy booth and $730 to operate the turkey leg booth, and so on. So this is what it would look like when we model this with a table. We can see that our independent variable is our hours, and our dependent variable would be the cost, the total cost per day in dollars. So if we define our variables, we let C represent the cotton candy booth and T represent the turkey leg booth, and H would represent our hours. If we look at putting these into equations, we would first have C, which is equal to the $16 per hour, which was given to us up here in the original problem. It costs $16 per hour plus the $500 per day for the food materials. For the turkey leg booth, it costs John $30 per hour plus the $700 per day for the permit and materials for that booth. And then if we look at the graphs, we can see that we've identified the cotton candy booth with the red and the turkey leg booth with the blue. So when we're looking at this red line, we can see that represents the equation here, and we can see it represented in the table here. We can see that the y-intercept is 500. That's our starting flat fee. And then we can see that the rate of change is $16 for every hour. With the blue line, or the turkey leg booth, we can see that its starting cost is $700. That's at 0 hours worked. That's the y-intercept. and then its rate of change is $30 per hour. If we look at problem number 2, it says how much more does the turkey leg booth cost per day? Model the situation using multiple representations. So we're going to now model the difference between the cost of the turkey leg booth and the cotton candy booth using the same representations that we just looked at for problem number 1. So if we look at the equations, we can see that if we subtract the cost of the cotton candy booth, we came up with the equation 16H plus 500 from the equation we came up with for the turkey leg booth, the 30H plus 700, we end up with a difference of 14H plus 200. When we look at this in the table, we see that the difference, if we look horizontally, for the daily cost at 0 hours worked for the cotton candy booth was 500, and for the turkey leg booth was 700. The difference between those two is $200. That's where this total difference comes from. It's the difference in our y-intercepts, or our starting fees, that $500 original fee just for materials per day, and the $700 for the permitted materials for, well, really just the materials per day for the turkey leg booth. So the daily difference in cost before they open each day is going to be this $200. The difference of 14 that we got from subtracting those constant rates of change shows up here. So this 214 we get by subtracting the total cost at 1 hour of labor between the cotton candy and turkey leg booths. The 228 is the difference between the total costs at 2 hours of labor. The second difference is what we call this. The second difference, or the difference of the first difference, is 14. And so we see that that difference won't change as we move down the table. And so if we look at this graphically, we can see, again, we have the blue line, which represents the turkey legs and turkey leg booth, and then we have the red line, which represents the cotton candy booth. And then now we've included this green line, which is the difference, the equation or the expression that we got, that is the difference of these first two original equations. Notice that when we look at the y-intercepts for the original two functions, and then we look at the y-intercept for the difference of those two functions, you can see the relationship between the y-intercept for turkey leg, the y-intercept for cotton candy, and now the y-intercept for the difference. It is in fact the difference of the original two y-intercepts. Likewise, the constant rate of change, the slope, is the difference of the original two rates per hour, or hourly costs. But if we look at the x-intercepts, we notice that the pattern here does not continue. It's not the same as the relationship we saw between the x-intercepts and the slope for each of these functions. And we looked at this back in Unit 3 when we explored the features of functions, and we were draining the pools, I think was the scenario. And so we were talking about if two different people were draining each of their pools at the amusement park, and they decided to combine their efforts and drain, if they could put all of the water in one pool and drain it all together using the two pumps, we kind of looked at how that would affect the x-intercepts and the y-intercepts and the slope. this is the same concept as what we looked at back there. Number 3 says, if cotton candy sells for $4 per bag, and how many bags does the owner have to sell to break even? So again, we have C representing cotton candy and H representing 12 hours of labor per day. And this was the original equation we came up with for cotton candy. So now what we know is the price per bag. Well, we know that the price per bag is $4, but we can't just substitute 4 in for our H, because that doesn't represent the price per bag. That represents 12 hours of labor. And we can't substitute the $4 per bag in for C, because C represents the total cost to operate the cotton candy booth. So what we're going to look at is how many bags, how much it would cost to run the booth for the entire 12 hours. So we're going to substitute in the 12 hours for H, and then we're going to simplify. And what we find is the total cost per day to operate the cotton candy booth is $692. Well, if that's how much it costs John to run the booth, now we need to know how many bags of cotton candy would he sell if he sells them for $4 per bag, so that he would break even, so that it wouldn't cost him anything to run the booth. He wouldn't make a profit, but it at least wouldn't cost him anything. So we're going to take that $692, or the total cost per day, and we're going to divide it by the $4 that he earns per bag. And when we divide that, we get 173. So he would need to sell 173 bags of cotton candy in order to break even. On the next page, you are asked to find the sums and differences of the 4 different functions that are listed. And so we're going to jump ahead to number 6 and take a look at the difference between the function h of x and the function j of x. And so they've given us these equations, and we're going to find the difference of those. So if we start with 3x plus 5 and we subtract the negative x minus 11, remember when we subtract a negative, that's the same thing as adding. So we have 3x minus a negative x gives us 4x, and 5 minus a negative 11 gives us positive 16. You should be able to complete the rest of these problems on your own. Good luck.